In the last video, we started how to create new distributions through different techniques like transformation, like mixing, like splicing. Uh, I think that video it's somehow technical and not easy, but luckily this is not the case for this video. Now we study section 2.4 Tail Properties. This section is relatively easy and we won't really go into a lot of details because the test points from this section are rather insignificant. So they are not important, and let's briefly discuss what tail properties are or tail properties we care about in this section. So first, you may have heard about like a fat tail, heavy tail, or thick tail, which I briefly mentioned previously. That's when we compare to normal, especially when we compare to normal. So if the tail part is higher or fatter than a normal distribution, we sometimes call it heavy-tailed distribution. So you must have a baseline to say whether you have a heavy or fat tail. So and the usual choice for the baseline is normal distribution. So basically, we want to know how big the loss can be, because to us it's only the right tail, because here we consider claim civility. So x is truncated, right, at 0. We only have x greater than or equal to 0, so you don't have left tail. So all you care about is the right tail of x. And the bigger the right tail, the more severe the claim is. So that's the reason why we actually care about the tail part of this x, because that's the most significant losses to an insurance company. So there are different things we can look at. The first property we look at is the how fast it goes to 0 for the survival function. So we know survival function is the probability that x greater than x, right? So as the value of the claim gets bigger and bigger, the probability gets smaller and smaller. Eventually, we know when x goes to infinity, this must be 0, and it is decreasing. So we will have something. If I draw a small picture, it should look like this. You should start with 1, right? So somehow decrease, right? Of course, it can go to 0 at different speed. Okay, so I might go a lot faster, say in the blue line, right? So this is a lot faster. Okay, when I approach 0. So the first measurement is to compare the survival function of two distributions. Here, S1 is the survival function of X1, S2 is the survival function of X2. So I'm trying to compare the speed of those two random variables approaching 0, okay? So of course, when X goes to 0, both will approach 0. So you have the 0, 0 case. One thing you can do is to apply L'Hospital rule, meaning you're going to differentiate for both, right? And to study the limit of the ratio between the derivatives, right? So that is the PDF. Here we have a quick example between Pareto and gamma distribution. So when we see this, we get something quite complicated. So I will not study this. So if you are interested, you can take a look. I only mentioned the result. So when x goes to infinity, their ratio also goes to infinity. What it means is x1. So what is x1? X1 is Pareto, right? So the probability of Pareto, okay, at the bottom is the gamma distribution, goes to infinity, which means Pareto is so much more heavier, than the gamma distribution, right? Because the density of Pareto is much, much bigger than the density of gamma when x goes to infinity. So Pareto is more likely to have bigger losses, right? So it has a thicker tail than the gamma distribution, which is not surprising, right? We don't even have MGF for Pareto, but we could have something for gamma distribution. Okay, so that's the result. Okay, so mathematically it's not interesting. So we just need to know some basic things. So here the basic things is we can introduce this measurement to compare the fatness between two distributions. Okay, so that would be enough. The next one we consider is quantile. Quantile obviously is important, but not here. It will be important when we study risk measures. This is value at risk. This is the famous WA. Used to be the standard of the industry, but not anymore after the financial crisis. So what is quantile? Quantile is the X value, that is a special X value such that the corresponding CDF at this value is equal to the percentage you want. So let me draw a graph, and so let's say this is my CDF. Okay, it eventually converges to 1. So let's say I want to know, let's say a big probability. So let's say this is 95%. Then the intersection goes to, here is X, right? This is a CDF. Okay, so this point is the quantile of 95%. So as you can see, this is the X value such that the CDF at this number, at this X equals to 95%. So that's why this is referred to the 95th percentile of X. So basically, this is a value such that this equation holds, okay? If you have a continuous random variable, you always have a unique quantile because your CDF is continuous and it's strictly increasing. But sometimes you may have flat part, like when you have discrete component, then you may have flat part, right? So you have, what do I have space? Let me draw it here. So let's say I have this, then I jump, I stay at this point, okay? I jump again, and then I somehow stay continuous. Okay, so the question is, let's say this is 70%. So let's hypothetically say this is 1, this is 2. So anything between 1 and 2 will give me 70%. So which number do I choose? Do I choose 1 or do I choose 2? Right. So that is the question. Most likely for us, we will use the left quantile. So it will be the smallest number such that we get to this level. Okay, but again, we will study everything in details once we get to the risk measures. So I'm not going to say things down here. The reason why we introduce quantile is this. Okay, we need to do some comparison. Not something this mathematical. So let me just draw a graph to help you understand why I need to introduce quantile. So let's say I have 2 distributions. So now I have enough space, so I'm going to draw it a lot bigger. So this is X. This is the corresponding CDF. So this is the graph for CDF. So I have this. So let's call this is the CDF of X1. Let's get a different color. So of course, eventually both graphs will converge to 1. So you can think somehow this point is 1, okay? So eventually when X gets bigger and bigger, both curves, both blue and pink curves will converge to 1. Okay, so this is my x2. Okay, so now as we use x to model the claim size, so now the question is, which one is riskier, x1 or x2? What would be your guess, right? So which one is bad for, or the worst for the insurance company if this is the model for the claim size, right? So then we can use the concept of Quantile to help us identify. Say, let's randomly pick a number. So of course it must be between 0 and 1, or 0 and 100%. So randomly pick a number. Let's say I pick a number down here. Okay, I draw a line. So call this delta. Delta is anything between 0% and 100%. Let's draw a line. Okay, so this is the quantile for x1. So let's call this small 1 delta. Okay, this is x2 delta. So obviously x2 delta is bigger than x1 delta. So x2 is riskier than x1. The reason is, so let's say delta, let's put a percentage. Okay, so what is the meaning of quantile? Quantile is the point to separate all the losses into, so here's delta, into 90% and 10%. So that means among all the losses of x1, 10% of the losses will be bigger than this number, okay? And the same reason, you can interpret something similar for x2 delta down here. So as you can see from here, because the quantile of x2 is bigger than the quantile x1, so his 10% is much, much worse than x1's 10%, right? Because it is on the right side. Right side is the bigger side, right? So the 10% of x2 are sitting at much, much bigger size, okay? Because here we have something down here for x1. So let's say this shadowed area, let's put a number. Let's say this is 9%. Of course, it does not look like 9%. And then we know the rest will be 1%, right? For the remaining part. Because according to the, this is PDF, so it's not the shaded area. So let me retreat this argument. We need PDF to see that. But anyway, from this comparison, we easily see one thing, that is, for x2, you have much, much bigger losses on the right-hand side, right? So that's why x2 is riskier than x1, although this line is actually sitting below. The one sitting below is those that are more dangerous, okay? Why? That's because, why this one is sitting below? That is because the higher one, the blue line, has more probability close to 0, right? So when we calculate the cumulative probabilities, it accumulates much, much faster than x2, right? It has more values on the lower side, so it accumulates faster. x2 is sitting below because most of the probabilities are on the bigger side, right? For bigger x's, that's why it's sitting on the lower side. So it's x2 is a riskier option, okay? You can also draw the PDF to help you understand this idea. So that is the reason why we need the quantile function to help us understand the riskiness of two random variables. Again, I don't think this part is very important, at least not here. Basically, you just solve the equation. So what you do is you try to solve this equation, right? So to solve for x, right? So this solution is the delta level quantile. So this is how you get the quantile. So basically you are solving an equation for the CDF. Sometimes it's doable, sometimes you can't. Like in the case here, you have to rely on the normal distribution table to get the quantile, or you can use any software. Okay. The next measurement is conditional tail expectation. So remember, quantile is only a threshold. Right? It separates the entire distribution into delta and 1 minus delta. We know those beyond the quantile, we have the probability 1 minus delta. We only know the probability, but not the severity, right? So here I give you two examples. So let's say x1 at, so let's use x and y. So I don't need to use lower index. So 95%, let's say is 1,000. So y 95, it is also 1,000, but the actual tail of x and y are different, which I will specify. So if I use quantile, there's nothing I can tell, especially if I choose the level to be 95%, then I don't know which one is worse, which one is better, because the value is the same. So the next level for me to do is to look at the tail. How worse are they on the tail for x and y? So let's say further I have, let's say x equals 1,500 equals, let's say 5%. So everything is on a single point. But for y, let's give two values, right? So let's give 1,500. Let's say I have 3%. Let's say y equals 2,000 additional 2%. So that's the entire tail. So from here we know this is probably not too good example. It should be 1,000. So basically, what we have done here is this. We know there is 5% of chance of seeing a loss more than 1,000, right? And in the case of X, it's degenerate. Everything is exactly located at 1,000. But for Y, the scenario is different. You have 3% at 1,000, 2% at 2,000. So if you only look at 95% quantile, they are the same, because according to this information, right? So the cutting point is 1,000 for both, right? Beyond 1,000, you have 5% for X. Beyond 1,000, you have 5% for Y. So they have the same quantile. But if you look at the CTE, the conditional tail expectation, conditioning on this part, okay, then things are different. Let's assume here I can take equality, because again, there's another trivial, not trivial, there's another delicate thing we need to be careful of. But in this case, since everything is located at 1,000, the mean is 1,000, right? For the tail part, if I only look at the 5%, the mean is 1,000. I don't need to average, there's only one single point. But here, okay, let's make things easy, 2.5, 2.5. So the mean, the CTE for Y is actually 1,500, right? Which means for both X and Y, there is 5% chance of seeing something bigger than or equal to 1,000. But in the case of X, if you see something like on the right-hand side, it must be 1,000. The average is 1,000. But for Y, it's different. You may see 1,000, you may see 2,000, and the average is 1,500. So it's bigger. The loss, the average loss beyond this threshold for Y is bigger. That's why it's worse. Okay? That is why we need to introduce the idea of conditional tail expectation. Looking at the threshold is good, but may not be enough for us to see the entire picture of the tail. And the CDE helps us to move one step forward. Of course, it does not give us the entire picture, right? It only gives us the threshold and the average beyond the threshold. Okay, and after that, I mean, it's possible that we have the same CTE, but someone, like one of them is more volatile, like have more values on the bigger side, like a variance is bigger, right? Then you need to study conditional tail variance. So, but you know, anyway, this is one step better than the quantile. Okay. I do not test CDE here, so I do not go into the calculation. Again, like I mentioned, we will study risk measures. In that chapter, we will get into every detail of quantile and CDE. So here, let's skip everything and leave to a later chapter. The final section 2.5 is the most important one. It is the foundation or one of the foundations of actuarial science. So we need more time to study section 2.5. So I will end here and continue in the next video.